always a pleasure to be here, to visit an old friend like Florent. Even if you stole people from ENS, we are still happy to come to visit. But come to France also, it's great. So the goal of the talk, so I will not, basically don't speak much about my own research. I would be just to zoom at one point on more hardcore mathematics with more recent research, but it was more to give a panorama of what I feel are interesting ideas from mathematics that have been used in AI. So a bit like mathematics for AI, which is very important, has always been very fruitful. And at the end of the talk, mention a bit the other way around, which I think we have witnessed in the last maybe 6 months or so, which is the crazy fast impact that AI has on mathematics. And I think it goes both ways. So I think I want to discuss this. I will give a bit of my opinion, my fear also, what are the possible difficulties we will be facing about research, but also teaching and so on. So I think it is interesting for this kind of two different aspects. All right, you can ask me questions during the talk. I would stay not very formal. I will write a few equations, but do a bit of name dropping. And if you have more precise questions on the mathematics, feel free to ask during the talk. Don't wait the last minute. So the first one, most of the part would be about ideas from mathematics that have been imported or used in AI. I'm not saying that mathematicians have invented AI or all the concepts we use in AI, they are actually been done by mathematicians. I would say it's fair to say it's not the case. But I think many researchers and results in AI, they are leveraging some interesting mathematical ideas of symmetries, way to represent the data, way to process them, that it's good to acknowledge and to see where it comes from. So this is just a timeline, I would say. It's good always to have some historical. So I would flash picture of my scientific heroes, to share them with me. It's like a classification in two, but of course it's much more complicated than this. This would be more like people from computer science or related field that have introduced more heuristical ideas that are key to the success of neural network. And this is my own choice. Maybe you would choose other key ideas that are really crucial in another day architecture. These are the ones I will focus on today. I think most of them you probably know. Of course, the perceptron, which are the baby or the initial ideas of neural network. Some are quite old, actually. For instance, I would mention backpropagation, which is arguably a very important algorithm. Then, of course, convolutional network, more recent architecture. So I think there is more and more discoveries as we go. Transformers is maybe the last incarnation of really great ideas that are very impactful. I'm just citing also ResNet and so on. And these are ideas I want to discuss. And then in red, I'm putting not really a one-to-one match, but related ideas in mathematics that we could discuss that are useful to understand these ideas. And I would go through them during the talk. But each time I try to pair, I would say, a computer scientist or someone in AI with, usually older, but not always older, people researcher in AI. And the last incarnation is Valérie, with my PhD student. There's many more people than Valérie that are working on transformer, but the young people, yeah, like you, the room, most of you are, I don't know, not everyone. I'm not young. But the future is yours, and I think it's important to keep mathematics in the loop, in particular in the view of modern architecture that are very complex to analyze. And Valérie is one of the talented young researchers that is trying to import ideas from mathematics, in particular here partial differential equation, to analyze transformers. Okay. Okay. I'm not going to say much more about this unless you have a specific question, and we are going to use through the talk this idea in more details. Maybe to zoom back, it's going to be a bit probably explaining things that you already know, that there has been a paradigm shift recently to what people call generative AI or generative learning, which is, basically a subclass of unsupervised learning that has taken by storm the community. So I think also one thing in the talk is to think about, different ways to represent or think about the data. Initially, I would say the big impact of AI in the last 15 years has been driven by supervised learning. Okay, unsupervised learning was useful, was certainly used everywhere before, but I don't think there was such a huge splash. I think one big splash of unsupervised learning was UMAP, for instance, or TSNE, a representation method that are super useful in particular. I work a bit on genomics, and I think it's fair to say that UMAP is used everywhere in genomics. If you look at papers in genomics, are using UMAP. UMAP is not really about deep learning, it's kind of a simple ideas, and it's definitely something super useful. So there's not only deep learning in the life, but I think it's still, considered as something that is pretty basics. Then came supervised learning, in particular AlexNet, as we're going to see, made a big splash, which is the idea that by scaling the network, having more data, but having very aggressive supervision, you could solve problem at the level of human performance, which was not clear at the time. If you look, 15 years ago, it wasn't clear. So I think there was a big realization. But then there's a big step that really, I think we are here today in the center mostly because of this. Call it the ChatGPT moment or whatever you call it, which is the idea of you move to self-supervision. So what makes unsupervised learning cool nowadays is you actually have a way to do the training from pure data. And I would say the two key ideas, I'm already spoiling my talk, the two key ideas of Gen AI, so there's like two sides of the same coin, is the way you would pre-train your network in the two particular setup. One would be like image generation, or like vectorial data generation, so not only images, of course it's like been extended in many ways, but the wow moment was stable diffusion, for instance, or this type of things that are applied to images. And here what you're going to do, hence the name self-supervised learning, you're going to create a fake supervision task, okay, which in this case would be denoising. So I think it's nice because I worked in image processing before, a long time ago in my PhD. And at that time, the problem were denoising. Everybody was trying to denoise images because in satellite imaging, in many fields in signal processing, you had noise and it was non-trivial at that time. Now it's considered trivial, but at the time it was considered a very hard and complicated problem to remove the noise. But I think it's good to see that research is a bit in cycle because we were studying denoising. Many researchers were studying crafting denoiser at that time, usually not with the neural network, sometimes with neural network. And now we are back for state-of-the-art Gen AI on images to learn denoiser. So it's nice to see that this fundamental ingredient, denoising, is still here. So it's good to still focus on it, understand, despite its simplicity, what this task is doing. And just to explain the obvious, what is the task? If you take a clean, so it's unsupervised, but of course you have data sets, you have clean images, you add noise and you add network without knowing the denoised image to come back to an image that is as close as possible. And this is something that we know how to do. I tell you, people have focused on this for years. We know how to do it. We know how to do it with neural network. And the cool thing that I would come back later is you can use it to generate images. And basically start from pure noise, and by denoising it, you will generate images. But at the end of the day, the training is like a fake supervised training thing. That is disappointingly simple. Okay, so I think you see me coming. The question is, you solve very simple tasks, very crazy dumb, and at the end of the day, you are able to do things that are actually useful. Particular, generate cats and dogs and whatever Ghibli images, but it's still something super. What I think is more impactful, I think generation of images is important. There are scientific tasks for which this type of method, the name is usually diffusion method, are actually used a lot, like let's say for proteins and so on. But what is very impactful in terms of industrial impact is, of course, for NLP, for natural language, where the community has been taken by storm, that by doing basically just a masking task, you are able to solve complicated tasks. So it's exactly the same idea that you create a fake task. What is this task? Is masking. So you mask part of the text and then you ask to predict the next word. So the next token prediction, that's a bit like denoising, a very dumb task. When you apply it in an autoregressive manner, you are still able to complete text and to solve complicated questions. So it's actually a mathematical question or a scientific question to understand why actually these simple tasks, they are able to generalize and to actually address, you can cheat at your homework, create poetry. And I would ask this at the end of the talk, possibly find new theorems in mathematics. Maybe do other scientific discovery, but go to things that are actually meaningful and impactful. So really, I think we are at local minima. We are very simple task, but it's a fairly good local minima that by actually solving this simple task, so completing text from left to right. Sometimes you have to realize how dumb it looks, but I think you should not be like Yann Lequin, like claiming that it's dumb, so it should not work. I think it actually at least partially works. So there is something very complicated happening under the hood when you complete token by token to generate a test. Call it reasoning. Now the buzzword is reasoning. I think maybe it's overselling to say it's really reasoning, but something complicated, probably a part of generalizing, is happening here. Okay. So, this is just a big picture. I'm not going to stay at this level of generalities throughout the talk, but I want to state the obvious that they are like very simple, very well mathematically defined tasks that we do on a daily basis that, I mean, seems to work remarkably well. So it's very stimulating for mathematician because it asks a very tough question. So I'm going to put open problem. Each of you can pick an open problem and try to solve it. So at this level, it looks like a bit too difficult to try to understand Gen AI, but you will see that there's a lot to go. So, I mean, whether you do purely supervised or denoising or masking, at the end of the day, you are going to do some form of supervision. Self-supervision, unsupervised, end of the day is optimization. What is also surprising at the mathematical level is optimization was considered, I mean, maybe 20 years ago, a bit old-fashioned. Students in mathematics, the optimization doesn't look so sexy. Nowadays, I mean, AI is optimization to a large extent. I think we would all love and hope that this could not be the case, that you could actually do interesting stuff in AI without doing optimization by doing something a bit more clever. Unfortunately, it's not really the case. I mean, there are fields for which you can do things much better without optimization. But even sampling, which looks like some generation of data, which looks like should not involve optimization at all, is actually done by optimization. And the mathematics of sampling, as witnessed in the last 5 years or so, is like merging with the mathematics of optimization. So I don't know, I mean, if there's a rule or not, that at the end of the day, you would have some optimization problem happening behind it. And the simplest possible optimization problem, but still relevant, Gauss or Legendre, publish or perish. So if you're French, you would probably credit Legendre. If not, maybe Gauss. The story is apparently Gauss had the idea before Legendre, but he didn't publish it. Then Legendre published it, and he actually did astronomical computation with it, least square. And then Gauss wrote it in a book after. So it's always like, I did it before you, but he didn't publish it on archive. So I mean, so let's call it least square, which is the idea of to design a predictor. So at the time of Legendre and Gauss, it was just a linear prediction. Of course, now we do nonlinear prediction, which from data, let's say noisy images, outputs hopefully clean images, and you're just measuring some notion of distance and some error. The most classical one being the least square. If you do like next token prediction, you're going probably to build some kind of logic predictor and do something a bit more fancy than least square. But it's going to be some error measure in terms of precision you do for denoising or prediction of the next token. Okay, at the end of the day, it's going to be this function. The only difficulty, of course, is that the function f would be crazy complicated, much more complicated than at the time of Legendre, where I did this with a pen and pencil to predict the position of stars. But it's the same ideas, the same mathematical question are still relevant. So what is the mathematical question? I mean, the first question is how do you minimize the function? And you will see it leads to a lot of questions. So you minimize, you have a very complicated function in a very high dimensional space. Clearly not a 2D function, but just to picture what you do. What you do is gradient descent. And once again, you do optimization, but rather than this, you do optimization with the same algorithm that we have been using for like 100 years. That's a bit unfortunate, but it's pretty much the truth that still doing local search, like looking in the local optimal direction, is still state of the art nowadays. So the gradient is the most important object ever. Okay. You should care about your gradient. So gradient is just, I mean, the partial derivative. It looks like this point is simple. Just remember that this vector, if you're training a transformer with billions of parameters, is a billion dimensional parameters. So I mean, just to state the obvious, that this is already something that just storing on your drive is going to be heavy. The question is, how do you compute it? Okay. Then what do? You do a loop. You just iterate over and over, stepping in the direction of negative the gradient to find your next update direction, which was once again not very innovative idea. You could quote, I mean, or cite a French researcher as usual, and Cauchy, for instance, studied this type of method and studies ordinary differential equation associated to this. In practice, of course, you do things a bit more fancy because your data is huge. So you would not take the full error. You usually use a few samples from your data, which is often called stochastic gradient descent, which I think is a bit of, I mean, a crime because it's not a descent method, because you replace your function with an approximation, a random approximation. If you know what happened during SGD, the error is doing this. So the name descent should refer to the fact that the energy should basically decay, but with stochastic gradient descent, you have fluctuations. So usually in mathematics, they call this like stochastic approximation, which is the idea of you have a gradient descent and you use random sample to have something that would be fractable. And I mean, I would not dive into the details, but of course, there's huge literature, huge body of theory of analyzing this, but it's not so new. I would say the one to credit are Robbins and Monroe, which are the one, I mean, really in statistics and probability actually, introduced the ideas. It was mostly theoretical at that time, but it's really an idea that have more than 70 years old, and it's still considered state of the art. With, I mean, a few remarks. The first remark I want to make at this level, don't underestimate the question of finding the step size. If you speak, and I speak to former students, unfortunately left for the industry, that really works in billion-dollar industry, which is like optimizing LLM at Mistral in French or otherwise in the GAFA. The key question they have on a daily basis, and I'm not joking, is finding the step size. Because obviously, if your step size is too small, I mean, life would be nice, it would converge to the minimum, but it would cost you billions of dollars because it's going to be too slow. So what you want is large step size, but it might devalue. If you too large step size, it will blow. And also for LLM, there are a lot of technical questions due to the, I mean, the fact that you have so many data. Okay, just doing even a pass through the data is enormous. So there's a lot of technical questions that becomes actually hard when it comes to selecting the step size, in particular because you are going to train a model. You probably don't want to wait 1 month or so to ship a version of your model. Maybe also you want to continue optimizing as new data comes. But you see, if you have a large step size, you're probably going to be very far away from the minimum. So there is like a tension, I would say, between, okay, let's use large step size to be very aggressive, but we also want small step size to have a good quality model, and you don't want to wait forever. So there are a lot of recipes that have been published, even if you look in the maybe last year or so, there have been tons of papers on step size scheduling. Very hard, difficult mathematical question. I'm not going to dive into this, but this question that was relevant at the time of Fushi is still even more relevant than before because of, won't lie, money issue in big companies. The second thing I want to mention, and I should also not underestimate how important it is that the storytelling that it's just business as usual. Okay, AI was the same 20 or 100 years ago is totally wrong. There has been tons of very important and impactful invention that makes AI system work. I would say the last, or one of the last ones to date, is ADAM. The ADAM optimizer, which was introduced by Kigma, is the one that is used routinely in training neural network. I would say before LLM, ADAM was useful, but not crucial. For LLM, ADAM is vital in the sense that if you don't use something similar to ADAM, so spoiler, ADAM is doing some kind of a weird normalization of the gradient, which we don't perfectly understand, but it's normalizing the gradient in a weird way. You don't have good performance. It basically doesn't work. And this is totally mysterious to me and probably to all the community. It's also hard because there is also a winner-take-all phenomena that if you come as a new player in the field with a new super idea about neural network, you would use ADAM and you would actually probably craft a neural network so that it works well with ADAM. So I mean, it's a bit like gradient descent on gradient descent because research is like optimizing the network, but also the optimizer. So it's hard to like really decipher what makes what work. And I think we should work more as a community on this. Like the basic question of why ADAM is working, not only converging, but converging to a nice network is one of the most important open problems of the field. And I don't see many researchers working on this. So advertisement for young or not so young researchers, you should work on ADAM, I think. Or at least maybe try to remove ADAM with something else. But what makes ADAM works precisely on the type of function we use in machine learning. Once again, I have no idea. And to be honest, I think it's hard, but it's a super interesting question. So, I mean, I just don't want to forget that there are research that's hard, and ADAM is used everywhere. I think the number of citations of ADAM, I don't know, it's like 300,000 maybe or something like this. But there's never been a paper in history of science that have rockets like this, because all the papers published in neural network, they are going to cite ADAM, which probably also means it's not a good idea because once again, it's like winner take all and we are reinforcing the use of an algorithm that maybe is not a good one. Checking time because I don't want to be too late. The second step is computing the gradient. It's very high dimensional because you want to compute the derivative with respect to all the variables. Okay, which means that computing the network is a priori already super complicated. It costs you maybe not millions of dollars, but it costs you a lot. Now, if I tell you compute the gradient and you want to compute all the derivatives, if you have 1 million parameters, it looks like you would need to compute 1 million times more things than computing the network itself. So if this was the case, if the computation of the gradient was more as complex as this, nobody would be in these rooms doing neural network. So what is the result that makes AI works? this result, I mean, I don't know who should be credited, but I'd like to credit, so I don't know how to pronounce his name, but Seppo Linaina, maybe, who proved this theorem during his master. So if you are a master or even worse, a PhD, you should wake up on this guy. He invented the algorithm or the theorem that makes AI works, like millions of people working because of his work that he did during his master. Well, okay, it was 50 years ago, so maybe life was easier at the time. What is this theorem? This theorem is really nice. It's nice in theory, and it's nice in practice. And I think it's hard. Usually theorems are good in theory, but doesn't work in practice, or the other way around. It's a theorem that works in theory and in practice. It says that computing the gradient is as complex and more or less like 2 or 3 times more complex than computing the network itself. Which means that, of course, when you compute the partial derivative, there are a lot of computations that are shared together. And this theorem is a way to optimally combine the computation to make actually computing the gradient as cheap as computing the network. Okay, and this is often called backpropagation or reverse mode automatic differentiation because the algorithm works by running a backward path in the network. I'm going to explain exactly, but this theorem is constructive. It's a theorem, when you do the proof, you have like a meta algorithm that takes your neural network and compute, if you want, a new neural network that computes the gradient. And this is behind the hood what you have in like PyTorch, JAX, and other like tools from AI. Tools from AI, they just like rely on this. I mean, they rely on 2 things: the fact that they work on GPU and the fact that they implement this ideas. So, of course, it's complicated to do on a large scale toolbox, but it is really it's my favorite. Honestly, I teach this. I think this should be taught, maybe not in high school, but I don't know at EPFL if there are people in the room like that are doing the curriculum for the course. Every course, not only in mathematics or in AI, should include this theorem. It's as important as like, I don't know, ghost pivoting. Pivot ghost is important. This is like the pivot ghost of AI. I hope you see me. So it looks simple. It's not as simple as it looks, and it's very deep. And credit should be given to people that basically use this theorem in theory for studying control, basically, Pontaglian, and in French. I love to say French researcher, Jacques Williams, who used it for, which is maybe the father of applied mathematics in France, that used basically this result for studying partial differential equation. But of course, they didn't do AI. So I think this is more or less what the people that should be credited. All right, so let's move forward because this is still very basic. About neural networks, I would go a bit fast because I mean these are like folklore results, not I would say not super useful on a daily basis, but those are good to know. So what are neural networks on a very I mean abstract level? These are just like chaining of linear transforms, so very simple transform, and ReLU or non-linear. So you apply a matrix, then you rectify it by ReLU and so on. So these are like architecture inspired by the brain, but in fact, there's nothing to do with neuroscience. I think the inspiration comes from it, that you do, the neurons are going to pull and then to do a non-linearity. Really the important things to understand is by stacking this very simple transform, you are going to build very complicated functions. I mean, a simple intuition that you can have is just in one day, and you have a ReLU network. If you put just one neuron, so here I just consider 2 layers. I just put the matrix with just one vector here. When you have one neuron, it's going to do something like this, with the key, which is due to the ReLU. And if you build more neurons, what it would do is we basically have more nonlinearity. So by pulling together what is called the width, having more width, what you would add is to have more nonlinearity. And intuitively, at least in one day, it's clear that you can approximate complicated functions. So the first theorem in the field was proved by George Sibenko, which is to say that with only 2 layers, like no linearity, not just 2 matrices and 1 ReLU, you can approximate any function. So you can a priori solve very complicated tasks. It doesn't tell you how you learn it, how the network is computed. It's like an abstract theorem. It's not very surprising. It's very boring. Doesn't tell you much about why it works. It just tells you that you can overfit. By putting enough neurons, you can overfit to any data. Can you generalize to unseen data? I mean, this theorem doesn't tell you. The other thing this theorem doesn't tell you, I mean, there's several things that this theorem doesn't tell you, like our open problem. What happens if you put more layers? I mean, of course, you would have even more nonlinearity, it would be even more complicated. So you can overfit even more, but is it useful or not? Until, I would say, AlexNet, it wasn't clear. I mean, neural network was not working very well before modern methods. So before this, it wasn't clear that this was actually useful. The other things that are open one, I'm flashing Linnaeus because he's one of the leaders in this field, and he has a nice theory about this, is what happened. So this time, tell you, this neural network exists. There exists a neural network that can approximate the function you want. In practice, of course, I mean, it's like mathematicians, it exists, but how do you find it? So usually you find it by SGD, I mean, what I've told you before. So is it true that SGD is converging? And practice, yes, I mean, if you run SGD, it always converges to neural networks that can overfit. I mean, if you put enough neurons and you use Adam or something that is nice enough, you can make the training error at almost zero. So it looks like there should be some theorem that say, if you have enough neurons, it always converges. This is the theorem of Linux. Linux proves that for two layers, it's true. If you have enough neurons, it always converges to the best possible, I mean, an optimal neural network. Is it true with deeper networks? This is unknown. It's believed to be true, but how to prove it, it's totally unknown. So you see, as simple as this question, they are still open in mathematics, which is good news. It means there's a lot of work to be done, but it's of course difficult question. Okay, I'm moving forward to, I would say, more modern. I say the first step that, I mean, we have witnesses, that's not so new, but it was key in AlexNet, is, of course, in practice, you don't going to use your vanilla Rosenblatt neural network. You're going to like use the invariance of the data to build neural networks that are more compact, more clever. And the simplest invariance is for images or like whatever vectorial data. You have like a translation invariance. Usually, if you want to do cat recognition or cat synthesis, you a priori has no preference whether the cat is on the left, on the right, and so on. So your network should be, I mean, actually invariant in some sense by this translation, let's call it this way, which means that if you have one neuron that is here, you should also have the same neuron at all the other translations. You should somehow factorize this neural network by saying the same neuron should be copied over and over. In terms of mathematics, if you look at what it means in terms of matrices, it means that the matrices are convolution, which of course is not new, and if you signal processing, it's not new. You could credit maybe Fourier. Fourier was one of the first that, I mean, studied this idea of like diffusion and convolution. I'd like to credit also Emmy Noether, because she did like the mathematics of invariance. What does invariance bring in terms of the type of function you have? Was for physics, but when you have translation, you would see that you would have convolution. And Jan LeCun is more or less, I mean, credited for bringing this idea to life in neural network. And it's started working once you have implemented it. So once you have basically used this idea of using convolution. But the burst, I would say, or the wow effect or the wow moment for learning, for machine learning or for AI was, I would say, in 2011, when these three, so Jeff Hinton now is a Nobel Prize, not really for this actually, for other discoveries, but this is the wow moment of deep learning, where this actually not very deep, and also at the time it was a deep network, but it's like a ridiculously small neural network, actually achieve like more than 10% increase of performance on ImageNet, which at that time was considered to be totally impossible. So they actually made impossible possible. And now I don't remember what is the state of the art on ImageNet, but you get like almost like perfect recovery. So convolution with like not very deep, but a bit of depth, a lot of data, training with HGD to high quality network. So you need a lot of training, really make a huge impact. So convolution invariance is the key. Leverage the property of your data, and this is just the tip of the iceberg. If you deal with proteins, if you deal with the graph, and so on, you would have other type of invariance, would mean probably you need to craft other type of network. For like images, people would use UNet nowadays, which is a way to also build invariance. I mean, I'm not an expert in generation of protein, but there are also tricks like this. So you need to put in your network as many information that you have. The second thing that I think is very important is the idea of depth. Of course, it has been told that you put deeper network, it will be better. Actually, at that time, this was not true. Okay, if you look at the paper after AlexNet, of course, they tried to put more layers, and at some point, it started to stagnate. So, or maybe the winter is coming, AI is going to collapse. What are you going to do? Because if you put more layers, so this is the standard architecture where you put 18 layers and then you switch to 34, more layer, worse performance. So this is a training error. This is not training, it's the test error during training, sorry. And you see that with more layer, probably the training error is smaller, but it generalizes less. Okay, the network is less good, is less unstable, more unstable. And so the idea is deep network like this are pretty unstable, very hard to train. What was the key result? Very disappointingly simple idea is the idea of the paper, it's called residual neural network, that now is used everywhere. So we don't even think about it. You put skip connection all over the place. The idea is during most of the network, you try to keep the dimension the same. Okay, For transformers, like it's the same dimension ever, so it's always the same dimension. For images, you don't do like this. You don't change the dimension every time. You try to keep, in fact, in ResNet, you have 4 big blocks, and during these 4 big stages, the dimension of the embedding stays the same. And because it stays the same, and I insist on this, you can re-inject back the input on the output. So instead of learning a huge transformation, you just learn the perturbation around the identity, which means if you put the weight at 0, you're doing nothing, which is not super good, but it's not super bad. Another way to think about this ResNet, so y is not equal to directly the network, is equal to x plus the network. So really, in terms of line of code, it's you change just x plus. Okay. What you can do is you can interpret this as a dynamical system. Okay. The network, it's moving the point around by small modification. Okay. So in terms of mathematics, this corresponds to the idea of differential equation. You can use this type of network, right? ResNet, as what people have called neural ODE, neural ordinary differential equation, as a way to approximate differential equation. So of course, it's not Leonard Euler that invented the fact that you should use ResNet for training, but they share like a common strategy, which is studying continuous deformation of the space. And it works. I mean, really impressive with ResNet. Sometimes it doesn't work better, but the performance, it's not a theorem, it's what happened in practice. The performance is not going to degrade with depth. Of course, if you do a network twice deeper, it's going to cost you twice more in terms of dollars, but at least you're not going to work worse, and in practice, you're going to work better. So this is the key idea, and I think it's as important as Adams. There are several ideas that are important that makes deep network works, and you see it's quite actually recent. Okay, so I'm always amazed that this was not discovered before. So it's like now it's not so recent, but maybe for AI it's considered to be very old, but really it's a really simple idea. So we are going to use it everywhere. Everywhere, all the networks are going to be super deep with skip connection. The last idea that maybe you are in the room because of this. I don't know how many people here work on NLP and basically use transformers. It's another thing that has taken the community by surprise, and I'm always amazed that each maybe 5 or so years, there is an idea that changes everything. So, and once again, the view that AI is like business as usual is not true. I mean, maybe, I mean, I don't know, people tends to be a bit like looking at the wrong side of the story. The good side is things are evolving super fast. They're always crazy, good, and clever ideas. The last idea is transformer. I think at the high level, the key idea of transformer is not necessarily the architecture, because architecture is the idea of tokenization. Tokenizing refers to the fact that instead of looking at your data as a big vector, like an image, you're going to break it into like small chunks, which are going to be the token. So for text, these are going to be a group of letters that you are encoding with a vector. With images, it's going to be small patch in your image. With protein, I mean, I'm not an expert in protein, but you have a way to tokenize the graph of the protein. I work in genomics, so you're going to tokenize the genes. So for each field, expert in the field, they have divided clever, let's call it, way to chunk your data into basically a point cloud. But at the end of the day, your data is going to be a big point cloud. Okay. Now, what is doing the transformer? I'm not going to go into the detail, but actually fairly simple, maybe even simpler than this like AlexNet with complicated change of dimension. You have your token, they live in some space of a fixed dimension. I don't know, but for DeepSeek is around 2000 dimensional space for the big model. So pretty high dimensional space. You get a lot of tokens. At training, you get 10 of thousands of tokens. At inference, and it's going to be the important part for the reasoning, you can get 100,000, millions of tokens. If you pay a lot, I don't know how they make you pay for the pro model in GPT, you would generate like millions of tokens. So really, this number of points is not like 6 points. It's imagine millions of points that is like a system of particles, like stars, that are going to interact together through the attention mechanism. So I'm going to go back to this equation after, but this is really the key novelty. It was not introduced in transformer. It was introduced 2 years before in NLP. The transformer paper just say this is the most important part. So basically, attention is all you need. I think it's a fake title because this is not true. In transformer, you have 3 ingredients, but really you use only this thing. So I think the transformer paper should be normalization, attention, and MLP is all you need. I think it would not be as nice, but these 3 ingredients, they are super important. In particular, you should not forget that in transformers, you have MLP. So Rosenblatt, 70-year-old MLP, they are still state of the art. I'm not kidding. If you look at DeepSeek paper, they still use 2-layer MLP And this is really the most important in terms of weight. So if you want to scale your transformer, which you don't want because you don't have the money, but if you would like to scale the transformer, what you need to scale is the NLP. Believe me, they have tried hard. They have found a local minima, which is big model to be good, you need larger NLP. So they would use mixture of expert trick to make it scale, but at the end of the day, the MLP is very simple but very important. I'm not going to speak about it because it's just what we saw before. It's going to process each token independently and map it through a huge MLP. Nobody will understand what it does, but at least it's important. Normalization, as its name suggests, is you just project your token on a sphere. So it's very boring, but also very important. If you don't do it, the attention will blow mathematically and in practice. So don't forget the normalization. The novelty is the attention, because the attention is what makes the tokens speak together. Once again, I like the metaphor of like particle system in physics, like in gravity, Newtonian potential. The tokens are like stars or planets. They speak to each other, and then they decide to which position they will move. But instead of using the law of physics, which is like this gravitational potential law, inverse of x minus y, here the law is the softmax law of AI. So you replace the Newtonian law by the softmax, which I think it makes sense because softmax is useful and used everywhere in AI. It's not clear why it's so poor. I just want to raise the question of why do you want to use softmax? If you change softmax by something else, usually it doesn't work. So, I mean, I'm not saying that this is like tiny details. And the softmax, and if you don't know what it is, it just refers to the fact that you compute the probability distribution through an exponential. Like exponential, and then you divide, it gives you weights that sums to 1, and you're just going to average your neighbors according to this distribution. But what is the key difference with respect to physics? In physics, the law is given to you by Newton or God. I mean, someone gives you the law, it's fixed. Of course, in AI, the law is learned. The way the interaction is computed here. You can look at the formula. It's a formula that depends on three matrices Q, K, and D. So this is not super important, just like rotating the points, but Q and K, they are the way tokens are speaking to each other. Okay, and for each layer, you would have different matrices. So if you want, an abstract view of transformer is it's like particles that interact together according to a law that is learned, is optimized. And this QK V, they reflect in probably what happened in language. I mean, the verb and whatever the pronouns are encoded here, and they're going to interact together to cook up a new position. And these matrices, there's less data than in MLP if you scale the network, but of course they are huge, and there are tons of millions of entries in this QKV. For each layer, and you usually have hundreds of layers, you would have a lot of matrices. I'm looking at time. So this opens so many questions. I mean, for me, this is like a dream for mathematician because nobody knows what's happening. So there's a lot of questions. In particular, what I will explain after is studying what happens when you have a lot of tokens. This is basically the PhD work of Valérie. In terms of expressivity, is it universal? What it means? In terms of training, the theorem of linearity, is it still true here? What's happening? I mean, it's like fast. So I think it's an opportunity for a lot of stimulating mathematics. Just to flash a few equations. I mean, if you're not a mathematician, just forget about it. Just to look maybe clever. What we do with Valérie and other people, we're trying, if you are joining the club, if you're interested, it's a nice club. we are nice. It's the idea of modeling token distribution as being basically a probability distribution. Exactly a bit like, I mean, you have many fields in physics, for instance, that study particle systems as probability distribution, maybe in quantum mechanics also. It's not really new. Of course, in Paris, you still have a finite number of particles, but you can view this particle as just a probability distribution over the set of tokens. What does it mean? It's basically, and you can even consider an infinite number of tokens. Let's be mathematician. Instead of having millions of particles, you could even say I have a continuous density of particles. At the level of mathematics, what it just corresponds to, you just replace the sum by integral. Okay, maybe you know that if you have a finite number of objects, you use sums. If you have a continuous density, you just use integral. So really, I mean, there's no real deep mathematics here. It's just to say that the transformer, although it's designed to operate over a finite number of tokens, mathematically, you can speak about what is called the mean field limits. What happened, and Florent is a representative of the community that is living by studying mean field phenomena, is studying the objects, even possibly with an infinite number of particles. It's good because it allows you to speak about many particles, even infinite, and it's also good because sometimes it simplifies the equation. Not always, but sometimes. In physics, it does. So here, what I do is I consider possibly infinite number of particles. And of course, what I do also, what I've explained before, is I do skip connection. I can also consider infinite number of layers. So it's continuous particles, continuous neural network, if you want. This is neural ODE. So if you don't know what is neural ODE, maybe it's not helpful, but it just corresponds to say that a neural network can be viewed as an ODE over the space of particles. And those who knows about maybe physics, they know that if you have particle system that follows an ODE at the level of density, so alpha is the density of particle, it corresponds to a partial differential equation. Okay, maybe you know about like Brownian motion, which corresponds to the heat equation. Here, it's more difficult. It's a nonlinear equation that I could call Sanders partial differential equation because Michael did this during his PhD work. You could call this the transformer partial differential equation. Which means that transformer, at an abstract level, they actually implement a partial differential equation that, unfortunately, is crazy complicated. This equation, I mean, it's not crazy complicated, but it's definitely not an equation that you can open your textbook and add the answer. So it's a good thing because I'm trying to stimulate mathematicians to work on this type of equation. For instance, Valerie, what she does, she studied this in particular cases to see if, in particular case, we can save few more things. And there is one case that, of course, is not very interesting for machine learning, but for which you can say a lot of things is for the case of Gaussians, which is arguably my favorite, maybe your favorite probability distribution, because it's a nice result, actually. If the tokens are distributed according to a Gaussian, imagine you have an infinite number of a text with an infinite number of tokens, and oh, by magic, they are Gaussian. It's never going to happen, but let's dream. Then during the transformers, the Gaussian is going to stay a Gaussian. You can just, I mean, it's a good exercise. Check that if you compute this over a Gaussian, it's very painful. Spoiler, GPT-5 solve it for you. So you can cheat and ask GPT-5. It would basically do the work of Valerie. But of course, you need, I mean, come on. The difficult part is not to answer the question, it's to ask the question. So if you ask the question to GPT, it outputs this equation, which is basically the evolution of the covariance. Covariance follows some equation that you can try to study, which is already not so simple. So even this equation is not easy to understand. And you have phenomena. For example, with Valerie, we identify some interesting phenomena. Sometimes the covariance could explode. Okay, sometimes the token could go to infinite and explode, which means that some token, which is what happened in practice, they could play a very important role. I don't know, in the sentence, there might be the verb is attracting a lot of attention because a token that grows, maybe should have said this first, in this attention mechanism, the word attention refers to the fact that if one of the xi or xj, sorry, here, is much larger than the other one, this exponential will be much larger, so it will attract a lot of attention. Okay, so this formula is really the softmax, for those who knows about like supervised learning, is a way to make some token more important than other one. So at the level of this equation, you can see this, that sometimes the covariance can explode, which means that some direction could like take the lead over all the other one. So, yeah.
Yeah. Two questions. One is, as you said, yeah, you're modeling tokens as Gaussian,
yeah,
with some covariance. And is there do you think that the direction would be to like compose this Gaussian with something that actually is language? Like,
so what we're trying now is to do like more experimental studies about the actual token distribution to understand its structure. So it's definitely not Gaussian for sure. Even a good question would be what is a good model to fit with what you observe in practice? It's not so clear. It's probably the other thing I should have said first is you also have a normalization layer. So here I'm forgetting about the normalization that of course constrains the token to stay on an ellipsoid. So there is also an interaction with the size of the ellipsoid. So I would say a good model, if you want to be closer to what happened in practice, is some kind of maybe Gaussian or something very anisotropic on an ellipse. But this is already like a tough model.
Do you think this is used? I mean, language like text, like human language, it's not going to be Gaussian, but people are using transformers for
yes,
physics, biology, all these things that might be more Gaussian.
Yes, so it's a good point. I think a crime would be to say everything is the same, should use the same model for everything. I think for text, there is also, I mean, for those who know, maybe I'm speaking to people in the room, but in NLP, you also have a masking. You need to be causal, which I didn't include here, so it's a bit like changing the token distribution. The tokens are discrete. I mean, you have a finite number, and you have a huge vocabulary, but the tokens are discrete. So it's probably very different from what happened in vision transformer, where here I think Gaussian would be, I mean, maybe not Gaussian, but a continuous distribution with density would be an appropriate model, which is also very different from what happened maybe like in genomics. So with genomics, where the token distribution, even the nature of the token is going to be very different. So I have absolutely no answer, but I think it's fair to say that it's probably not possible to have a common model for everyone. So I say the architecture is the same. The distribution, the normalization, and so on, they are probably vastly different, which means that the equation itself maybe should be different. So I mean, I'm totally agree. I mean, I'm just saying, I mean, don't take this for granted. It's just like a funny computation that is nice, but it's not going to be super useful. But you are young, dynamic, focus on this, try to find good models, and finding good mathematical model is already super interesting. So I have less than 10 minutes, so let me try to give a few, I would say, reflection on what happened nowadays in a reasoning model. I've already speak a bit about this, but let be a bit more precise. So by first, generative AI, I already said this, I'm going to skip this slide. There are two kinds nowadays of Gen AI. The one for vectors and the, I mean, let's say for images on the right, which is diffusion model. I'm not going to speak about it. It's super interesting. If you have, with my talk this morning in the summer school world about this, there's a lot of nice things to say, but really I'm going to focus on text where the big fuzz is happening, in particular in mathematics. So just don't forget that there's several Gen AI. Of course, everybody's trying to merge them together. I mean, in the future, probably there would be diffusion model for text that works. It's not yet there. Okay, so nowadays the state of the art by far in NLP is still next token prediction. Despite this, it still does crazy things, and in particular in mathematics. I think, I mean, maybe 2 years ago, or maybe even 1 year ago, it was unclear. But nowadays, if you're a mathematician, or even, I mean, someone that is interested in like having some rigorous reasoning with a LaTeX file and an equation, it's breathtaking. It's breathtaking. Why? And not really clear why. Because it has been pre-trained for data generation, let's say, by next token prediction, where you can still use it to solve problems that maybe some of them have been already seen. I mean, it's clearly, it has seen all the homework you can imagine. So if it's just to solve homework, maybe it's not surprising, but it can clearly do some partial reasoning. It can clearly extrapolate outside of its data set. This is a phenomenon that is very hard to analyze because of data contamination. Okay, it's very hard to bench this because each time you post a solution on the internet, it's going to be used very soon by OpenAI. So just don't be confused by press release. I mean, there are a lot of press release, even of researchers that used to work with us, and don't want to say anyone that is saying that, oh, it's crazy, it can solve mathematical questions like this one. I mean, yeah, but maybe it's just some question that has been solved on archive, and it's just like Google 3.0, and it's already super useful. I'm not speaking about this. I'm speaking about use it for your research. Use it for questions that you're pretty sure that it's not copy-paste from archive. And you would say it's able to do stuff by copy-pasting probably existing reasoning, but in a clever way. This is just an example just to illustrate how the workflow is going to change forever. And the workflow is you're going to do mathematics, whether you want it or not. Maybe you don't want to use AI. I think soon, maybe unfortunately, all the community, I say mathematics, but researchers that do theory to a large extent would be fueled by paper generated at a large extent by reasoning model. And I think it's inevitable. We just have to be prepared for it and see how we can go with it. Because these reasoning models, they are not made by us. I mean, we have to be careful that we researchers don't control the way they have been trained, which is problematic. It's just to express the workflow currently. I'm not lying, this is a very painful workflow. You iterate between prompting, LaTeX, maybe Python, and I mean, it's nice because I mean, the LLM can understand everything, even like Mathematica, even NumPy, even I mean, all the language that you want to use in mathematics in general, you can use it. At the end, you have your paper on archive, you're happy, and the process is painful, but at the end is able to do stuff that are very impressive. That I think, I mean, I'm very surprised. Before the O3 model of OpenAI, I don't know about you, but for me, the eye-opening was the O3 model. Really, with the O3 model, you could witness that you could do research in mathematics with this, which was not the case before. Before, honestly, it was useful to do emailing or to do like database summary, not to do reasoning. Nowadays, it works. It works, I mean, and I'm here. It's a bit unfortunate that I'm only crediting GAFA, but this is really driven by GAFA. Right? So maybe there is the opportunity for us to move. In particular, there was a press release. It's not, I mean, I should have updated my slide. Was a press release by DeepMind a while ago about like having like silver medal level, whatever this really means, because they use a lot of tokens, are a bit like cheating. But they can crack at the time silver model silver medal level at the Olympiad of Math, which is basically like not very advanced mathematics, is like high school mathematics, but questions that are hard. I mean, if I ask you in the room to solve this question, I mean, you would not be able, you would have to really work hard. These are non-trivial problems that has never appeared online before, really created for this. So you really need to think, and this model, I mean, the alpha reasoning model was really like exploring the proof strategy a bit like AlphaGo. And this was already surprising, but more recently, I didn't put in my slide, but there was press release by several companies that claim gold medal with, I would say, standard LLMs. So LLMs that generate tokens in an informal mathematical way, which I think is already a good indication that even with classical LLMs, so by this I mean next token prediction LLM, are able to do something that can solve, we don't know how, but high school interesting question. And high school means it's already useful for us because in mathematics, I don't know about you, but most of the questions I ask, they are like high school level. I'm not like solving the field medal conjecture all the time. So I'm rather like a bit more modest. I would still be very happy to have a very clever high school mathematician that can solve in a microsecond all my problems. Now, the question is, what is the future? And it's not clear. So the future, I mean, it's already happening. I mean, I think you see me coming, is reasoning models. So what currently is the state of the art of model? They cost a lot. They are super painful to use. You have to wait for like 2 minutes to have the answer or even more. You have to spend, I don't know what is the price for GPT Pro, but it costs a lot. The future now is generating millions of tokens. By this, you allow the network to generate a lot of tokens, and it works. So it's scaling works. I don't think it's only scaling, it's scaling plus new training strategies. So I think the interesting part is you train it, of course, by next token prediction, but you also train it with reinforcement learning techniques, which means that they also evaluate the quality of the reasoning. Okay, this requires like a lot of, I mean, this is like very costly to train. So, I mean, it's a question whether us as academics could play a role. But definitely this question of introducing more complex learning strategy because you want to do mathematics is super useful. And I think it's why mathematics is going to fall first, because these are fields for which you can at least evaluate a bit more easily the answer than if you were a philosopher. If you're in philosophy, it's very hard to say, is this reasoning good or not? In mathematics, there's a question for which means the answer is yes or no. I mean, this is a dumb question for this. I mean, you could just give a reward, which is, was he able to predict the value of some computation? But with, this would be a way to introduce this, with formal proof language like Lean, Coq, and so on, you can actually evaluate reasoning. It's a bit like mathematics is like coding. I mean, coding LaTeX, but at the end, if the proof is correct, it's exactly like a code that is compiling. So just the fact that not even the proof is correct, but just the fact that the reasoning compiled is already a very good reward. So mathematics, unfortunately for us, I don't know, is going to fall, I mean, or at least it's not going to be the last field to be cracked by AI, or at least where big advance will be made, because it's a field that is very, not simple, but at least can be formalized easily, much more easily than physics, chemistry, and biology. So biology is probably going to be the last, I mean, or very difficult to make big advance through only AI. For mathematics, I don't know. I mean, I don't think gold medal means that mathematics has been cracked, but I think it would be cracked when all the papers on archives, they are going to be generated by AI, which is going to happen at some point, meaning that all the mathematicians, they will rely on the technology to generate their paper. I bet you that in 5 years, it's going to be the case. At some level, at the same level that we use, I don't know, Word or Excel or LaTeX to generate things. And it's going to be a tool. We are going to use it. We are still going to need mathematicians. I'm not saying that they are going to replace it, but to a large extent, all the technical details are going to be done by this LLM. And my experience, I don't know about you, but in the last 6 months, I witnessed, I mean, much better quality in terms of reasoning, and things start to be actually super useful. I think my time is over. Just to say that there's not only mathematics, there are a lot of other fields that are being impacted. I work a lot on biology, and I think you should, because it's very important, as important as mathematics. And for this, I think LLM has still a long way to go. I think there's, of course, there was the AlphaFold moment where it's starting to see some impact, but AlphaFold is like really like the tip of the iceberg. All the remaining part of the biology, we don't even really know how to train LLM. For astrophysics, there have been a lot of very nice results recently. I'm not an expert, just flashing you a recent paper by Flatiron. It's moving fast. There might be fields for which training LLM might actually work. There might be fields for which it's not. And the reason, I think I can conclude on this, is it's not clear what is next token prediction for genes. I mean, what is going to be the training task which is going to generalize outside? For text, next token prediction seems to work very well. For images, denoising seems to work very well. For genes, denoising genes, what we do, doesn't seem to work so well. For astrophysics, I mean, I cannot comment, maybe there are. So I think one question is what is the loss function you want to use to impact other things? And I would stop on this open question and thank you for your attention.